The question is, how do we measure security, and how did I get here is sort of a lot of, well, it's been a path, a long path. The premises, shit's broken. And that's really kind of, I could do the entire presentation just on those two words. Fundamentally, people don't realize that we're using a security model developed in 1972. Shit's broken. We have nothing else to do. And one of the angles that I take, and that's why I call the work I've been doing for the last 19 years analog network security, is because we have been misthinking the entire problem. And of course, I'm going to have, in my humble opinion, after every single sentence. Part of your job also is to call out my bullshit. If I say something you don't like, raise your hand, call me, and you may get a book if it's a really, really good question. Otherwise, I'll let you deal with Eric. I grew up in this world, an analog world. My mother was an analog engineer. My father was an analog engineer. That was my first beer at DEF CON, way the hell back. I used to repair TVs at age 6 because all it involved was pulling tubes, going down to the drugstore, finding the bad one, putting it back, and I'd made 50 cents. And for 6-year-olds in the 50s, that's pretty good money. And so my father taught me engineering on a regular basis. That's what an electronics store used to look like in my day. And that was the first computer I ever built, and it was an analog computer. And how many people actually have ever used slide rules? How many people have heard of slide rules? All right, those are analog computers. They give you close enough answers, and that's how we got to the moon. We didn't have much of anything else other than these analog things. High school and I never really agreed with each other very much. So at 16, I decided to go into systems engineering instead, and went into the record business and got to do all sorts of cool mechanical stuff, kinetic stuff, cyber, such as it was in the analog world back in those days. And this is the cutting lathe on how we used to make vinyl discs. I got to work with Hendrix and Robert Moog in early analog sound effects and synthesizers. This was all analog stuff. And we used to have to make patterns like this, match, in order to synchronize audio and video before the standards of SMPTE came out. And this is going back into the 60s still. And then I got out of rock and roll and decided to become a security expert. Back in '83, there weren't too many people in this field. But I got hooked. I got hooked by the whole idea of security through doing some work with encryption with a company you may know as Western Digital. And I knew nothing, but I pitched myself as a security expert and got a few gigs out of it. And then decided to destroy the internet by writing books like this, Information Warfare, Terminal Compromise, that showed how we were going to end up in global conflict. Here's the technology, here are the procedures, here's how it's all going to work. And if you've heard the phrase electronic Pearl Harbor, I'm the one to blame for that. And so this all goes back some 30 years. And ultimately, we're still no better off now, and perhaps much worse off, even though I and a number of other people were ringing the clarions back in the early days of shit's gonna get bad out there. But we chose to do absolutely nothing about it. So we all need to fix the internet. And we were all working on various ideas. And then the book there, Time-Based Security, was the first foray into something that gave us a little bit of mathematics on how to do it. And that book actually got started in a Polish bar in Warsaw trying to convince apparatchiks they were unable to control their users in the new type of economy and politics that were occurring in Poland in those days. So throughout all of this, I wanted to prove that security could be done, that you could actually mathematically prove security. And I'm seeing a lot of skeptical faces out here, and I love seeing them because I'm going to walk you through some of how we get there and give you a taste of all of the mathematics that are actually behind all of this. So I'm saying security actually can be measured. We've just been looking at the problem entirely wrong. Does anybody in the room believe that we can create a secure thing?
I believe we can.
You can? You can have 100% security.
Yes.
You believe it?
Yes.
Unplug it? Is that the unplug it argument down here? Okay, fine. Take people out of the equation. Then we have technicals, 100% security. Anybody? 100% security. So the only thing I've done in this case is say, we're going to eliminate the number 1 from any discussion in security from now on. And at the same time, we're going to eliminate 0 because we're approaching security with a digital binary mindset. And that is the fundamental flaw by which we have been going down this road. And trust, the same thing. Do we have, or can you say you have absolute 100% trust in any person, in any kinetic or cyber system? Your spouse, 100% trust. Why are you grinning at me like that, sir? Don't you like your wife?
100%.
Can we say 100%? And the answer is no, of course not. Can we have 0? No. But what we can do is approach them. And in calculus terms, that's called a limit. And this is going to be the bedrock of how we look at security from an entirely different approach. So first thing we're going to do is kill absolutism. I absolutely refuse to do anything absolutely. Now, is that a paradox or is it infinite recursive? You can look at it either way, but that is what we're not doing in security right now. Excuse all of the screw-ups on this because I came from a Mac to a PC and something happened to the PowerPoint, so apologies. So what we're going to need to do is employ some different ways of looking at systems. Now, all of the systems we're going to talk about are what I call anthro-cyber-kinetic. There's human components, cyber-electronic components, and kinetic components. And those are the 3 domains in which we all live. So any security solution is going to have to work in an abstract way across all 3 domains, whether they're functioning in isolation or in some sort of system. Makes no difference. So we have to redo our philosophical bases and beliefs. We're going to have to insert feedback. And I'll get into that in a little bit more detail because in our industry, we do not use anything to control our systems from getting out of control or running into chaos. We just don't do it. Yet everything else on the planet does from an engineering standpoint. So we're going to start here, and again, I apologize for this. This is where we kind of are. The fortress mentality, especially the military, going back to the early work in the late 60s, early 70s. We're going to build walls so high the bad guys can't get in. In isolated, non-networked conditions, did I have 100% security? No, because I still had a fence, a lock, a guard, a dog, all of which are potentially defeatable when you do a proper risk analysis. Yet still, this was in isolation, in a non-networked environment, things are a lot better. So let's say I've got that castle, or maybe we can do it with a pawn shop or a jewelry store. The jewelry store has a nice, big, thick plate glass window. How much protection does that provide the jewelry store from theft of all of the diamonds that are in the window?
Near 0.
Near 0 is what this gentleman says. Anybody else? Sorry?
There's still a door.
There's still the door. Who said it depends? It depends upon what?
Whether there's police.
Whether there's police. Are police protection?
No, but their response.
Their response. So it's not protection. No. So your firewall in the electronic world, does that provide 100% security?
No.
Why not?
Because
Well, how much does it provide?
20%.
20% of what? You're going to lose this argument. You aware of that?
I can lose this argument in one of 2 ways.
Fair enough. It provides some degree of redirection of hostile forces, is effectively what we're doing with protection. So let's look at it from the time domain, and we're going to put time into everything we talk about. That glass window in front of the jewelry store, how much time does it provide in protection?
How long it takes to break through it?
How long? So we'll say a second? Okay, so then the bad guys are just going to take everything and run off, right? Yeah? In theory, what's going to happen after the window's broken? What? All right, break the case. That's another second. We're into 2 seconds. This response. What do you have before response?
Just trying to back up to one thing, right? So you said that firewall gets up what percentage of protection? I think my question would be, what's the acceptable risk level? Right?
We're going to get there.
Because you can
We're going to get there. I
historically, how much that-
promise you, we're going to get there. You're already 40 slides ahead, but you're spot on thinking. 50, 60, who the hell knows? What we have before response is what? Detection. And then we have response. So in the physical world, PT, protection time of this window, approaches 0 because of the size of the brick that we happen to have. How long does it take, in this hypothetical jewelry store, detection to take that the bad guys just broke in? Sorry? Electron, okay, you pick it. So we'll say pretty damn fast it should be. All right, so we'll just say a second there. Then how long does response take? Depends where you are. So what's a decent number for whether it's the security guard company or the cops? What's a good number? 2 minutes?
Half an hour.
Half an hour. I'm gonna be kind and go with 2 minutes. So what we end up with is, from a mathematical standpoint, PT, protection time, is indeterminate. We don't know whether it's a firewall. We don't know whether it's psychological breaking of the human, creating a vulnerability. We don't know exactly, but we can approximate in the physical world how much protection in time we have. So what we end up with then is 2 numbers, DT, detection time, and plus reaction time. And in this case, we've got 2 minutes and 2 seconds for the bad guys to take 2 minutes and 2 seconds worth of stuff before there's a response. There, sir, is the beginning of your risk evaluation based in time. Now, if all the stuff in the window aren't diamonds and they're glass, your risk is going to be different for obvious reasons. Fake files, redirection, what have you. So the goal that we have is to make our detection and reaction time as small as possible. Whether we're in an anthro, a cyber, or any kinetic system, doesn't matter when we're looking at security, because the ET exposure time is where we begin to consider risk. How much risk do I have? And the only way to bring ourselves from the risk and trust world over to the security world is through the common denominator of measurement of time. And we're going to keep using time over and over. When we look at the bottom formula here, BW divided by IB DBI, that tells us in a cyber world what our risk is in terms of time versus data loss, data exfiltration, vis-a-vis the bandwidth of the system. So static data still has a time component in relation to your system. None of them sit in isolation. They all work together. So, great pictures here. Feedback, up in the upper right, it's an electronic system of using negative feedback in order to keep a system from going out of control. Earlier you heard the feedback acoustically that occurred through positive feedback because the volume was too high. And that's putting a system into chaos, and that's what we experience there. Same thing can happen electronically. Anybody know what the picture is of that physical device? It's a feedback mechanism called a governor that was used initially to keep trains from running too fast, and it would maintain the speed below a particular velocity that was predetermined by the tracks and the engine. And this was inside of a case, and you've heard the phrase balls to the wall. It comes from this, because as the train speeds up, the balls pull out with centrifugal force and approach the wall of it, which says you can go no faster. Balls to the wall has a legitimate 18th century derivation. SCADA systems all operate on the same premise that there is no 0 and there is no 1, and everything in the middle is variable using feedback. Have to have feedback in any system to be able to even consider some sort of measurement at all. So we live with these things. We're designing these things, and we've had them around us, except for some reason in the world of cybersecurity, we've ignored fundamental engineering principles because software and cyber are far superior to everything else, and a good coder can design his way out of anything, right? And that's why we're in the mess that we're in now. So, same thing we've got with neural networks. Neural networks are analog functions. There are no zeros, there are no ones, and in addition, inside of a neural network and AI systems, there is zero memory. Zero memory. So every time you put an input to an AI system and get an output, it's an entirely new, unique measurement with no guarantee of getting the same results twice. So AI is a whole different talk, but be careful when you get into that world. However, this is still completely an analog function, and I'm trying to get people to realize how this is all kind of coalescing into the same. There we go. So in network security, again, we're very linear, very, very linear in the way we think, until the point when chaos hits, and then that's the nonlinear junction of something in the system going bad, and because we don't have mechanisms for detection of chaos, that's why systems go crazy periodically, whether it's caused by humans or the systems themselves. All right, network security is a bear. And this is also part of the fundamental issue that we have here when we're measuring systems. There's the bear. So there's two guys, and one of them stops to put on some really good Nike sneakers, and the other guy says, "Why are you putting on sneakers? How's that going to help you? You got to run from the bear. You got to run faster than the bear." And the answer is no. I only got to run faster than you. Which is the premise of feedback in systems. And since we're in a military world here, or area, everybody familiar with OODA loops? OODA loops? A few of you. Observe, orient, decide, and act. It's a circular process that lets you survive aerial combat by getting inside of your adversary's OODA loop, which is explicitly time-based. Again, another mechanism that we're going to be able to use. So OODA loop was designed it was here in Montgomery by John Boyd in the 1980s. And if you've never read the paper, please read it, because it is astoundingly brilliant for its day. Yet, what do we do with OODA loops and feedback in our systems today? Once in a while, you'll see a piece of it here and there, but systemically, we totally ignore it. And you can get all sorts of complicated later on. So when we're talking about neuroscience and humans in the equation, these are all analog functions as well. There are no zeros, there are no ones. Everything is in between, with protection being the indeterminate value. And this gives us the basis by which we can start examining how to do measurements. So let's take a look at this one. I use this, it happens on my bank, probably happens on some of yours now. You initiate a process on your phone or on your computer, and it says, "I really don't know who you are, you got to prove it to me." 2FA, out-of-band authentication. There's a pause. And that pause is an analog function of time that will tell you you have 10 minutes to enter in a code we're sending to some other known device. As long as you do it within 10 minutes, you get a no-go, no-go decision based upon the amount of time it took you to respond. If it takes longer than X amount of prescribed policy-driven time units, you fail. And you either get your hand slapped, got to do it again, or whatever else they've decided. This is a time-based feedback network, which is what 2FA essentially is. And we're integrating the two of them for this particular application. Feedback, out of band, and time. All analog functions. So now, with a car, anybody have an automatic driving car yet? You do, what do you got?
It's a Corolla.
A Corolla. Corollas are automatic?
Yeah.
No, I don't mean the engine, I mean the whole car.
Oh.
No.
Never talk about transmission.
To the back of the room, dude. You are definitely not getting a book. You're doing a good job.
I know.
We have one of the new Subarus, and it tells you when you're moving out of a lane, and it tells you all this stuff, and it's got cameras and things and notifications. This is the logic that is used for that. So, hypothetically speaking, before we had automatic cars, you want to turn the lane, you put on your blinker, and what do you do next? Look. Now, with automatic cars, what is the tendency? To trust the technology. The text, if eyesight says there's no car there, I believe it 100%, right? Because you know there's an asshole in a Porsche coming down your butt at 140 miles an hour. And the eyesight's not going to detect it. You, as a human detection system, will be able to. And all of this is a feedback loop with decision time, which traditionally is that we're trying to automate, and it's not going to go so well for a while. So we're already tempting to use this sort of stuff. So, trust issues, because we're going to get into the gentleman's concept of risk a little bit more now. Trust, we do not have absolute trust in anything. We cannot, for all the obvious reasons. What we can do, though, is weight the trust. And this is sort of it's a matrix, which is a poor man's neural network, if you will. This could be applied in AI as well, where we've got lots of criteria, and then we weight the criteria. How important is a particular function, attitude, whether we're dealing with a human, a cyber system, or a kinetic system? How important are each one when we are trying to establish a layer of trust? And this becomes very, very dynamic, as you will see, because the dynamicism happens to be called degrading curves. And these are all simple mathematical functions that are exponential, linear, or logarithmic decay curves that occur over time as part of just the way nature is. So you can end up with trust factors of, in this case over here, we got what, 0.779, we got 0.918. Now keep in mind that the trust factors that are established in any design or policy-driven organization, his are going to be one set of numbers, his are going to be another set of numbers. We don't have the cross-pollination figured out yet for these. But within specific constrained, bounded conditions, you can apply trust factors very, very easily, which will then get back to the risk issue. So, how do we start thinking about this? Boolean logic gives us very, very discrete, binary, digital kinds of thinking. So we got AND gates, NOR gates, we got all those various types of gates. But what we don't have is the feedback mechanism, nor the analog component into it. So we had to create a new type of truth table, which tells us all the varying conditions that can exist within a given circuit. And in this circuit's case, all we're doing is something very, very simple that comes from the concept of the two-man rule. Alice wants to do something. Alice can be a person, can be a process, can be a motor, can be a switch, doesn't matter. Alice wants to do something, makes a decision. That creates an action. That action is to invoke the decision in some cases, or to perhaps wait until Bob approves. Now, if Bob's on vacation, well, that may cause some trouble. Bob's out to lunch, I need it now. This is all a function of time. How long, in order to maintain the amount of trust I have in Alice, based upon the prior trust factors that we've established for Alice, Bob's got his level of trust factor. How long are we willing to wait for this to occur? At the code level, it could be 10 clock cycles. In the human world, it could be hours, days perhaps. We trust Alice enough to let Bob verify it in 2 weeks, 2 hours, whatever is decided by policy. This is the core circuit that is used to be able to create time-based feedback mechanisms for high-speed detection in networks, or human processes, or kinetic systems as well. This engine, we all fly in these. When's the last time an engine caused an airplane crash? Anybody? Right, yeah, it's been a long damn time. These engines have 5,000 plus detection mechanisms in it, sampling at least once a second. Our networks, can anybody make a similar claim? Why? We're running the planet on these networks. What happens when I have 5,000 detection points going on without going, oh, does anybody know the answer? What happens? What is one of the huge benefits that I get if I have, in this case, an engine with 5,000 detection circuits? Get quick response, yes, but that's, what is a huge, huge benefit? Reaction time, huger. Redundancy, that's part of the system design initially. Anybody? What? Detection is there because I got 5. I have the ability to predict the future. When you have enough detection points that are going on inside of a well-engineered system, a failure or an anomalous behavior in any one of them is a predictive value of what might happen. To be able to tell the pilot, oh God, engine number 1 just had this and now it's this. Safest thing to do is to turn it off because I can still fly on one engine. We don't want to, but we can. Having enough information allows us to predict the future, which is what we as humans do every single day of our lives. Yes, sir?
How does that change when you have a process that you don't know what the output will be?
If you don't know, if you don't know the output, that's a separate problem, isn't it?
When we're getting new technologies over there, we know what the possible failures are. So if we have the engine detection, we then have to figure out, compile that to figure out what this will lead to out failures, and to go from there.
Gonna get there.
We're gonna have to-
Gonna get there. 2 good questions. We're gonna get there. So, let's talk about a vendor product. And we're gonna talk about detection, because detection is the key of this whole thing with time and bounded conditions of zeros and ones as functional limits. So I got a black box up there, a Splunk box, a SIM box, IDR, IPS, I don't care. So what we're gonna do is just allow good traffic in. We all know what good traffic should look like. This is an easy benchmark. We also know what the vendor tells us. The vendor says, we can pick up and detect all of this stuff. Okay, maybe they can, maybe they can't. I'm not gonna argue that now. So let's take what the vendor claims they can detect, and inject it into that same traffic stream with the good traffic. But what we're gonna do at the same time is start a clock. And that clock is gonna begin at 0. Gonna inject it into the black box. Now, if the black box does not detect the hostile traffic, we have a condition of time equals infinity or approaches infinity. And that is where chaos begins. So let's take that off the table for now and say the black box properly detects the hostile traffic I've put in. As soon as it's detected, it stops the clock. That time value, that formula down there, tells you that in that given hardware, software environment, detection time. So we can test vendors' products right now. All the detection guys that make all these wild claims downstairs. Anybody a vendor, by the way? Anybody willing to admit it? And up there on the right, it's a simple limit formula. Because one of the questions is in this black box, all right, if I can detect this hostile traffic, we'll say 1 millisecond, making it up. What happens if I improve the hardware? What happens if I give it more RAM? What happens if I increase the cores on the CPU? Will the performance be better? Will it not be better? Will it be a linear or nonlinear progression? How do the environmental test bed conditions affect the amount of detection time it actually takes in a real world environment? We now have the capability, this is a few lines of code. And we're doing some of this research now over in Holland in universities to start figuring out which products are really good and which ones are not so good. And we're finding differences of 2 orders of magnitude in performance of vendors who we're not naming yet. Does everybody get this? Because this is absolutely core to where we're going to go. How simple it is to measure detection. Any questions? Yes, sir.
You said the limit is the efficiency is the key. You said the efficiency is the key. Can you explain the limit?
Oh, the limit is you're just going down, you're going to have a limit of 0. That's it. Everything is a functional limit, and in this case, we want dt plus rt, well, in this case, dt, to approach 0. It never will hit 0. There's no such thing as instantaneity. That's all. Okay? So, now we can do the same thing with detection and reaction. Basically what happens is we stop clock 1 after the system detects it, start clock 2, and that's where the response process occurs. We use the word an awful lot in our industry, remediation, and I'm not very happy with that term. I prefer response, satisfactory response to the policy, because that may be remediation, it may not be remediation. The response is immaterial as long as that response is satisfactory for that particular condition by design. So in this case, we have 2 clocks that are measuring what is going on from detection and reaction. And again, the formulas down there are very, very simple. And we can benchmark this in a heartbeat. Now, when you're doing process and procedure that involve humans, there are slightly different physical techniques you're going to need to use, but the principle is exactly the same, because remediation may be automatic, in which case it's going to be very fast, hopefully very fast. You'll be able to measure it electronically. If it involves humans, you're going to have to take all of those things and then strongly define what a satisfactory response to a detection is. Entirely up to you how to do it, but the formulas are there, and again, it keeps PT out of the equation. We don't care if you have 1 firewall, 10 firewalls, or any protection mechanisms at all, because those are of indeterminate value. And once things are of indeterminate value, what do? The bad guys, 92% of all successful attacks begin where? What kind of endpoint? People. So we're putting trillions of dollars of all this stuff in there, yet they're going after the wetware. So the process doesn't matter if I'm an anthro-cyber or kinetic. You have to design your remediation or response process in order to just fit into these formulas. You can design to the numbers. Now, in this case, we hear often companies will say, we're going to use 2 products, so we're sane about it. That way, if product A doesn't get it, product B will get it. Is that a good thing or a bad thing? What? Yes. Who said that? That almost requires a book. Why is it yes?
One of those conditions has to be true.
Not entirely true. Okay. There are. They can both be true. Is that, you sure? You sure?
Yes, I am sure they could both be a good thing and a bad thing.
Okay. Let's look at it from a slightly different viewpoint. I got these 2 detection boxes of some quality, and we have measured them already independently using that prior slide, and we're going to say that the value that we trust that that is going to occur is 0.9. It's an arbitrary number. Now, I have these 2 boxes. I need to make a decision based upon the results coming out of these 2 boxes. So the question is, do I want an AND gate requiring both boxes to come to the same condition or determination, or do I want an OR gate where I will then react to either one? Which condition do I want? Huh? Or, why?
Because the AND gate could create more false positives.
Because the AND gate can create more false positives. All right, the mathematics says it's the other way around. Because we're in a probabilistic world, because we have no 1s and no 0s. So everything else is in the middle. And when we apply Bayesian probability to it, the AND gate up there, when we do an AND gate, and require both devices to agree, the efficacy of that particular detection system goes up by 2 orders of magnitude. We're in a probabilistic world here. We're no longer in a deterministic world. When we do an OR gate, the math shows us that we end up with about 10% less efficacy and trust in that particular system's process. So we've been doing this fundamentally wrong for many, many years. And again, the mathematics supports every single bit of this. So from a data exfiltration standpoint, we can take a very similar approach. So we have an SMTP server of some sort, and we'll just call that the exfiltration channel for right now. But when traffic is leaving, how much of that traffic is actually examined? So let's say we have a detection mechanism in our SMTP traffic, and it's looking for stuff like XLS sheets with salaries or customer lists, or I've sent it to an entire address book of people. Anomalous behaviors that some companies actually do play around with. How should we handle this? All we want to do in order to verify that the data to be sent out or avoid exfiltration by a hostile is delayed by the amount of time it takes that detection mechanism to find or clear that SMTP traffic from being hostile. How long does it take? 100 milliseconds? 5 seconds? I don't know the answer to that because I have not played with the SMTP filters yet. But there is a given amount of time that it's going to take to give us a given amount of confidence in or trust in the particular findings that that detection mechanism has. So now I put a delay in. That delay has to be a little bit greater, a little longer in time, than the amount of time it takes the detection mechanism to actually make a determination. What happens now? What's the result of that circuit? Anybody? Anything that your policy is programmed into your SMTP servers not to allow or out of the organization, you're detecting it and delaying it before it leaves the organization. It's still under your control versus doing the examination either in side channel parallel in the same time domain or afterwards saying, oops, look what Sue in finance just did. And all it takes is a little bit of delay in one circuit while you're doing what you're normally going to be doing anyway. Phishing, same sort of thing. User clicks on stupid shit. What should your computer do? Your computer should go into a pause mode. That pause mode is the amount of time, a little bit greater amount of time than it takes your phishing detection box to say with given level of confidence, probabilistically, it's a phish, it's a bad website, it's a good, whatever the determination is. If you create the delay in the process before the click is initiated and the action is taken, what is the result? What? You have increased it, but more important than that. What happens to phishing? It's going to go way the hell down by orders of magnitude because you're doing the detection and the delay before the bad stuff happens. And if the vendors make their products appropriately working fast enough, what happens? The user will never notice what's going on in the background. So the circuits are very, very simple. Adding an out-of-band channel takes the same approach when we're looking at network-to-network connectivity or internetworking. Right now, TCP/IP is a great thing, isn't it? Beautiful thing. Well-designed, isn't it? Well, TCP, it works sometimes, yeah. It has a unique paradoxical characteristic. It's one channel, one wire. So you don't have to run 2 wires. That's a good thing, right? Except when you cut it. because you're cutting both the data channel and the control signal on the same hunk of wire. That's not the way ICS and SCADA systems work. They operate completely differently with outside, out-of-band communications. Two-factor authentication. We're sort of doing that with the banking example earlier. An awful lot of SCADA systems using out-of-band communication. The jet engines, they're all out-of-band detection mechanism channels that are independent of the process that is being done, completely independent. So in this case, we're going to have a network, and it's going to have what we're going to call a detection reaction channel for detection reaction, which may or may not include remediation. So right now, everything's working wonderful, except when I get DOSed, my primary communication channel is also unable to talk to the next hop, isn't it? And what do? We pick up the telephone. We have out-of-band processes, which are the only ones left to us. However, if we had a parallel backbone to the existing global, we'll call it tier 1, tier 2 infrastructure, using the detection reaction speeds and everything we were talking about earlier, we can have those messages with an independent protocol sent up from hop where the effect is being DOSed up to hop 1. And they'll say, hey, I'm getting some really bad traffic. Can you get rid of it? And what is one of the greatest skills that every ISP on the planet has? They can filter anything they want. So that's a no-brainer. I'm seeing this, I'm seeing this, I'm seeing this. Take care of it. Thanks. Now, the internet is effectively, even though we don't think of it that way, is a closed system. The internet is a mesh network. And when you examine how tier 1, tier 2 global networks work, there's very few, very, very few dynamic relationships. Most of them are static, and there are very few in number. So it's very easy to look at how a detection reaction matrix would work in a given small closed mesh network. So in the case of solving DOS, what I want to do is now hop 1 has filtered the stuff so the guy now can at least get back online up to him, but ISP 1 now knows where that traffic's coming from, doesn't he? So what should he do?
Block it.
Tell the parallel partners, hey, I'm getting this funky traffic that messed with that guy down there, and I don't know, all 5 of you should know about it. Now, ISP2, what does ISP2 do? Repeat. ISP3, repeat. By putting in the detection reaction systems, we're able to have remediation automated on a back channel. And what does that do to DDoS traffic? What does it do to spam? And what we're doing is introducing that dynamic analog flip-flop and delay lines. And that keeps everything in sync, and it would put everybody into the same process. So, can AT&T do this all by themselves? No, they can do it within their own little network. We need AT&T, we need Nippon, we need China, we need Australia, we need everybody to play, because the numbers, according to AT&T, who we're talking with now, this would reduce 97% of their backbone traffic. So they'd be kind of happy about that. And this is what it all would look like cascaded out with the clocks, with the delay lines, and with all of the bits that are the decision-making processes, where each ISP is going to give another ISP a given level of trust, degraded over time, of course, which then requires the recursive revetting periodically. We call this, in OODA terms, squeezing the loop. We want all of these time components to do what? Approach zero. That's our entire goal. We are not going to ever make a system secure, but we can take elements of it and make each one approach zero. We're working on AI stuff. I'm not going to go through all that stuff right now. This is what security looks like with a logarithmic decay. There's linear decays and exponential decays as well, and they are all based upon a single concept of feedback and detection. We also have to realize that we are well beyond 6 sigma if we're going to be anything efficacious in our world. So we're going to be dealing with trust factors, that are going to have 10 nines and 12 nines, depending upon the efficiency, the time efficacy, and all of the components in this. But we're going to end up with curves that look like that we have actually already turned into sound. So you know how submarine guys can say, oh, that's the Russian NC-35 sub. We're looking at potentially having engineers being able to identify security problems sonically using this technique. So in OODA, the winner is the fast guy. So from Boyd's viewpoint, if I'm faster than my adversary in a dogfight, I'm going to win and I will survive. The guy that loses has a slower OODA process. All we're doing is taking all of these concepts and applying them to the world of security with the different types of results that can occur with the math and the entire mathematical formula that for every bit of what you've just seen is this, and it has been vetted by NSA, CIA, mathematicians around the world, and that is the security formula for designing proper systems. So you can do some of this stuff right now. You can go home and play with it. You can make it work and see how your vendors are doing. Does your vendor even know? When I talk to vendors about this, they run because largely they don't know. They don't like the questions. And that's one of the best questions you can ask your vendors, is the ones that they hate. Because in this world, all we care about is speed. Here is the Crash commercial plug. Please buy a lot of my books. It's completely outlined there, all the mathematics. And there were two great questions that I've got to give books away for. And I'm here to answer anything that I loved your snarky ass answer there, sir. And the fact that you predicted where we were going to go with trust and risk factors and joy. So that is the high level on how to look at measurements of your systems, how to apply it in design. The mathematics is trivial, notwithstanding that formula up there. Each application is really fairly trivial. It's a set of bounded min-max conditions, and that's it. And we've missed it for 60 years. So thank you very much. Any questions? I am here. Any group questions? I'm happy to try to answer and respond.